Now that we've talked about enthalpy, we need to talk about measuring enthalpy, or measuring the heat flow in and out of a system. The process we're going to use is called calorimetry. Calorimetry is the measure of heat flow in or out of a system. The word calorie, you saw a term that you're probably familiar with, measuring in food quantities. What a calorie in food refers to is how much energy is required by your body, or how much energy that food provides to your body in kilojoules. Now, calorie is a unit that's been converted from kilojoules, and in food, when we measure calories, it's actually in kilocalories with a capital C, which is 1,000 calories. But we don't actually say that a Snickers bar, for example, has 250,000 calories of heat required, or energy that it provides for you. We say it's 250 calories with capital C, because obvious reasons. If people heard they had 250,000 calories, they'd go crazy. All right, so calorimetry is a process of figuring out how much heat is lost or gained by a system. Now, in order to do that, we have to know the specific heat of certain substances. A specific heat is the amount of heat required to raise 1 gram of a substance 1 degree Celsius. So, for example, if I have 1 gram of water, how much energy, or how many kilojoules or joules of heat do I have to require to add to that to raise that 1 gram sample by 1 degree Celsius? Now, for water, that number is 4.18 joules per gram degree Celsius. That means it takes 4.18 joules to raise 1 gram of water 1 degree Celsius. Every substance has its own specific heat. There's a small table on page 246 in your text, table 6.2, that has some specific heats of certain substances there, and if you need to use them. And then there's many indexes out there that have lots of different specific heats of substances. Now, the heat capacity of a substance is the amount of heat required to raise a specific quantity of a substance by 1 degree Celsius. So it's looking at, if I have a 50-gram sample of iron, or if I have a 100-gram sample of iron, how much would it take to raise that whole sample by 1 degree Celsius? Or if I have a frying pan, how much energy does it take to raise that frying pan 50 degrees to heat my food? Right? So that is heat capacity. It's slightly different. Now, one of the things we can use this for is to determine specific heats, or determine how much heat is lost by a substance. And the equation we use is Q, which again is heat, equals to M, stands for mass, times specific heat times the change in temperature. Or Q equals heat capacity times delta T. For example, an iron bar of a mass of 869 grams cools from 94 degrees Celsius to 5 degrees Celsius. Calculate the heat released by the metal if the specific heat of the iron is 0.444 joules per gram degree Celsius. Well, in this problem, we're calculating heat loss. So Q equals mass, which is 869 grams, times specific heat, which is 0.444, times our change in temperature, which is 94 minus 5, which is 89 degrees Celsius. When I solve this problem, my answer for Q is not going to be in kilojoules, it's going to be in joules, because specific heat unit is joules per gram degree Celsius. So when I punch in my calculator, I have 869 times 0.444 times 89 equals 34,339 joules. But when I move the decimal, that makes it 34.3 kilojoules. All right, so this is the first use of calorimetry. Calorimetry is used to figure out the amount of heat lost or gained by the system. And again, Q is the amount of heat that's flowing in or out. It can be calculated by mass times specific heat times the delta T. In the upcoming sections, we're going to look at 2 specific types of calorimetry and how they're used in chemical reactions. The first type of calorimetry we're going to talk about is called bomb calorimetry, spelled like the word bomb, B-O-M-B. Bomb calorimetry is a process in which combustion reactions are measured to determine how much heat is generated as a result of burning a certain fuel. This is the kind of process that is used to determine calories in a food sample as well. The diagram here shows you how things work, and if you look at the diagram, there's a containment vessel, and this containment vessel basically is just there to make sure that the heat is insulated and everything is kept inside the system, and any dangerous things are there. The bomb itself is this little device down here, in the bottom of the pan. Inside that, what it is a stainless steel container, and inside that is a small pan right there that you can C, they put a fuel in there. And what happens to the fuel is you put the fuel in, you then run a spark, or you run an ignition wire to the top, and then the ignition wire is also connected to ground. And what happens is that you fill this up with oxygen. There's an oxygen inlet valve right here. So it gets pumped full of oxygen because oxygen is needed to combust things. And we make sure we have enough oxygen in there to be the excess reactant. That whole thing is then submersed into a tank of water of a very specific mass. It's very measured. You would know exactly how much is there. So for example, you know there's 4.00 kilograms of water in there, or 4,000 grams of water exactly. And that's the calorimeter bucket. It's an insulated bucket. Thermometer goes in so that we can measure the temperature change of the water. Now in theory, what happens is, as we ignite the wire, this device starts to spark down there, and then it starts to burn. It will burn in this container. The device has what is called a heat capacity of the calorimeter, or CCAL is what we refer to that as. It's understood that the heat capacity of the calorimeter is telling you how many kilojoules of heat are going on inside for every degree of Celsius that's transferred out to the water. So if we can measure the temperature change of the water, we can figure out how much heat has been lost by the calorimeter, and therefore we can figure out how much heat was generated by the reaction. Now, in that, the calculation is very simple. The heat capacity, or the heat of the reaction to reaction, RXN stands for reaction, equals negative CCAL times delta T. CCAL is a very specific number, and it is given to you for the calorimeter. It would have been carried out in a previous experiment. For the purpose of this class, we don't have to worry about that. It will be a given in a problem if you need to know the heat capacity of the calorimeter. All right, so let's look at an example. A quantity of 1.922 grams of methanol was burned in a bomb calorimeter. The temperature of the water rose by 4.20 degrees Celsius. If the heat capacity of the calorimeter was 10.4 kilojoules per degree Celsius, calculate the molar heat of combustion of methanol. Now what the molar heat of combustion is saying is they want to figure out how many kilojoules there are per mole of methanol. All right, so in the combustion of methanol, how many kilojoules are generated per mole? Well, the first thing we do is we start off by calculating our Q. Q equals negative CCAL, which is negative 10.4 kilojoules per degree Celsius, times the change in temperature, which just happened to be 4.20 degrees C. Erase that and redo it. Times 4.20 degrees C. All right, so using a calculator again, we simply put in there that we have negative 10.4 times 4.2, and the heat that would be generated is negative 43.7 joules. All right? So that's how many joules were generated. Now, once we have that, the question doesn't ask us how many joules of heat are generated. It asks us what's the molar heat capacity, molar heat of combustion of methanol. That's how many joules were generated for 1.922 grams. So once you calculate Q to get the heat capacity, you'll either be asked for two things, kilojoules per gram or kilojoules per mole. Once I get that would be 0.0437 kilojoules. I simply need to divide that by how many moles of substance there are to get kilojoules per mole. So on the side, I take 1.922 times 1 over the molar mass of methanol. Methanol has 12 for carbon, plus 3 more for hydrogen is 15, plus 16 more is 31, plus 1 more for the hydrogen is 32. So 1 over 32, if I put in my calculator again, 1.922 divided by 32, I get 0.0601 moles. So if I come back down here, and I enter my values now, 0.0437 divided by 0.0601 gives me a molar heat capacity of 0.727 kilojoules per mole. So the combustion of methanol produces 0.727 kilojoules per mole, which really isn't a lot of heat. All right, so one of the problems we have with methanol and ethanol and gasoline is that it doesn't generate the heat that oil products do, or gasoline does. So when you have gasoline that has ethanol added, you hear people say that it's less energy efficient. It's cleaner, but it's less energy efficient because it doesn't generate the heat that is required that gasoline does. All right, so this is the first type of calorimetry called bomb calorimetry. Again, as a review, it's used specifically for combustion reactions only, and you use the equation Q to calculate how much heat is generated in the reaction, and then you divide by the moles of the reactant, in this case the methanol, to figure out the kilojoules per mole for the reaction. The second type of calorimetry is called coffee cup calorimetry, or constant pressure calorimetry. It's called coffee cup calorimetry because frequently it is actually carried out in a coffee cup or a styrofoam vessel. In coffee cup calorimetry, it's generally used for determining the calorimetry of reactions in solution phase, which is the majority of our reactions. It's used for a lot of other things too, as we'll see here. In a coffee cup calorimeter, we assume that we have an isolated system. So we're assuming that the heat lost by a reaction has to be equal to the heat gained by the solution, or the negative heat of the solution. So whatever's happening to the solution, if the temperature of the water is going up in a solution, that is basically entailing the fact that the reaction is giving off heat, so therefore the reaction must be negative or exothermic, and vice versa. Because in an isolated system, the heat of the reaction plus the heat of the solution has to equal 0. Because an isolated system means there's no energy or no matter exchange with the surroundings. Now, that being said, let's look at a very first example of how we use the coffee cup calorimetry. One of the uses of coffee cup calorimetry is to determine the specific heat of a substance, or an unknown substance, or a known substance. In this case, we have a lead pellet having a mass of 26.47 grams at 89.98 degrees Celsius. We take that piece of metal and we drop it into a coffee cup calorimeter that has 100.0 milliliters of water. When we do that, the temperature of the water rises from 22.50 degrees Celsius to 23.17 degrees Celsius. From that, we want to figure out the specific heat of the lead metal. Now, what do we know is that the heat of the lead has to be equal to the heat gained by the water. So the heat lost by the lead has to equal the heat gained by the water. Well, earlier we learned that heat can be substituted for mass times specific heat times delta T. So the mass of the lead times specific heat of the lead times the change temperature of the lead has to equal the mass of the water times the specific heat of the water times the change in temperature of the water. All right, so we're assuming a perfect transfer of heat. Now, we know the mass of the lead is 26.47 grams. We're trying to find specific heat, so we'll leave that as that. The change in temperature of the lead, we're going to assume, went from 89.98 degrees Celsius down to this temperature. That is called the equivalence point. So if the water rose to that temperature, we're assuming that that's the end point that lead changed to that temperature. So minus 23.17 degrees Celsius. Which means the change temperature was 66.81 degrees Celsius. Now for the water, we had 100 milliliters, and we know that water is 1 gram per milliliter, so we can assume that 100 milliliters is 100 grams. The specific heat of water is a number we always know, which is 4.18 joules per gram degrees Celsius. And the change temperature of the water went from 23.17 up to 23.17 from 22.50, so a difference of 0.67. All right, so given the variables we know, we plug in what we have, and we can calculate specific heat of the lead. All right, we do so by simply saying, calculator, 100 times 4.18 times 0.67 equals, all right, so that's the heat of the water, divided by 66.81 divided by 26.47 equals. And when I do that, I find that the specific heat equals 0.1677 or 168 joules per gram degrees Celsius. All right, so that's the first application of using the coffee cup calorimetry and figuring out specific heat of the substance. And in that case, when you're asked to find specific heat, you basically use the assumption that the heat of the metal or the object is equal to the heat gained by the water, and then you set up the problem just as we just did. Now, the second way we can use this is actually to figure out the enthalpy change for a reaction. So when we were doing thermochemical equations, that enthalpy change on the equation, we can figure that out for a chemical reaction by simply doing some coffee cup calorimetry. So in our example, we are going to take a quantity of 1.00 times 10 to the second milliliters of hydrochloric acid, 0.5 molar hydrochloric acid, and we're going to mix that with 100 milliliters of 0.5 molar sodium hydroxide. The initial temperature of both the hydrochloric acid and sodium hydroxide was the same, and it was 22.50 degrees Celsius. The final temperature when it was done reacting was 25.86 degrees Celsius. So again, we know the heat of the reaction equals the negative heat of the solution. So we're going to measure the solution in this case to figure out what happened in the reaction. Now, since the temperature went up, what we can learn is this. Anytime you have a coffee cup calorimeter and the temperature goes up, you know you're going to have a delta H value that is negative. If the temperature goes down, the delta H value is going to be positive. Nowhere in the calculation will it give you a negative sign, or it will always be a positive because its overall changes. So keep that in mind. You have to attach that negative sign as you go through. Now, we start off by simply taking Q equals M times delta T times specific heat. The mass is the mass of all reactants and the water. All right, so in this case, I have 100 milliliters of hydrochloric acid, 100 milliliters of sodium hydroxide. We're going to assume that they have the density of pure water since they're relatively dilute solutions. So we're going to assume that we have 100 grams of water, HCl, 100 grams of NaOH. We're going to have 200 grams of reactants. Now from there, the change in temperature went from 22.5 to 25.86. So 25.86 minus 22.50 gives me 3.36 degrees Celsius. Okay, so change in temperature. Water, which is what we're measuring, has a specific heat of 4.18 joules per gram degree Celsius. So again, from this reaction, I find that I have, if I pull my calculator back up, 200 times 3.36 times 4.18 gives me 2,808 or 2,809 joules, which is 2.81 kilojoules. So that's how much heat is generated by the reaction. Now the question is not again asking us how much heat is generated. It's asking us to calculate the delta H. Delta H is measured in kilojoules per mole of reactant. All right, so kilojoules per mole of reactant. In this case, we would have to determine what the limiting reaction is. But since we have the same number of moles of each thing and it's a one-to-one reaction, I know that if I have a 0.500 molar solution and I have 100 milliliters or 0.10 liters, I can figure out my moles as 0.05 moles of either reactant. I have 0.05 moles of sodium hydroxide. I have 0.05 moles of hydrochloric acid. So in this problem, it doesn't matter. So for the hydrochloric acid and sodium hydroxide, if I take 2.81 kilojoules now, divided by the moles of reactant, I will get my kilojoules per mole. So again, now I pull that in there. I have 2.81 divided by 0.05, and it gives me 56.2 kilojoules per mole. Now, I, again, can see there's no negative sign in my answer, but this is an exothermic reaction, and as such, I need to put a negative sign in the front. So you do need to remember to keep track of the sign. So negative 56.2 kilojoules per mole. The negative sign is telling me that the reaction loses heat. Now, if I ask to calculate kilojoules per gram, like you may be asked to do in some cases, you simply take kilojoules divided by the grams. So in this case, if I had 0.05 moles of HCl, I could multiply by 36.5, which is the molar mass, and then get grams, and then plug that in down below. All right, so yet another example of how we use coffee cup calorimetry, which is to determine enthalpy change for a reaction. Now, adding into your notes, which is not there, is another one where we're trying to determine the heat of dissociation of a reactant. Heat of dissociation basically refers to how much energy is involved in dissociating a salt or dissociating a substance in solution. In our example, we're going to take water in our coffee cup calorimeter, and we have 200 milliliters of water, which means we have 200 grams of water. And we're going to add to that 5 grams of sodium chloride. So I have a spoon here that has 5 grams of NaCl. When I combine them, I'm going to watch the temperature change of the solution. And again, the heat of the reaction will equal the negative heat of solution. So whatever the reaction is doing, that must be gained by the solution. So if the reaction is exothermic, giving off heat, the temperature will go up, and therefore the reaction will be negative. I have a negative value in front of my answer. If the reaction, the temperature goes down, that means it's endothermic and it's drawing energy out of the water. So if I put the water in here, so I dump into 5 grams in the solution, and the sodium chloride starts to dissociate into sodium ions and into chloride ions. All right, just we learned in chapter 4. Now, when that happens, we want to calculate how much heat is per mole and per gram. So we're going to calculate how many kilojoules per mole and kilojoules per gram are associated with that dissociation. So Q equals mass times delta T times specific heat. When you do these problems, the mass is the mass of the solution plus the reactant. So it's 200 grams for the water plus 5 grams of reactant, so it's 205 grams. The change in temperature went from 25 down to 23.89. So the temperature dropped by a total of 1.11 degrees Celsius. Now notice I didn't put a negative sign because it's change in temperature, not direction. There's no negative or positive involved. That's why we have to remember to put the sign on the end. And again, water has a specific heat of 4.18 joules per gram degrees Celsius. So from there, we take our calculator, we punch in 205 times 1.11 times 4.18, and I get a value of 951 joules for this reaction, which is 0.951 kilojoules. All right, so that's how much energy is generated out of that, and it's endothermic because the temperature was dropping. So we know because the temperature went down in the solution, it's endothermic. Anytime, again, you have a solution and the temperature drops in a solution, you have an endothermic system, the temperature raises, you have an exothermic reaction. So in this case, the dissociation of sodium chloride is endothermic. Now, we know the kilojoules, but the question asks us to calculate kilojoules per mole and kilojoules per gram. Now, to get kilojoules per mole, we're going to simply take 0.951 kilojoules. We're going to divide by how many grams. So let's do the kilojoules per gram first. So we have 0.951 kilojoules of energy for every 5.00 grams of sodium chloride. So we would get, again, bring the handy calculator up, 0.9, oh, bring it back down, 0.951 kilojoules divided by 5 means I have 0.190 kilojoules per gram. All right, so it's 0.190 kilojoules per gram. Now, if I want kilojoules per mole, I, again, take my grams, or I take my 0.951 kilojoules, my 0.190 kilojoules per gram, and I know for sodium chloride, there are 53.5 grams, sorry, 58.5, I got it wrong, grams per 1 mole. So now again, if I take 0.190 times 58.5 gives me 11.2 kilojoules per mole. So the dissociation of sodium chloride would generate 11.2 kilojoules per mole in solution. All right, so it actually is absorbing heat out of the water. It's a positive endothermic reaction. All right, so there are 3 examples of endothermic, solution coffee cup calorimetry. Again, coffee cup calorimetry is only used in solution phase. Bomb calorimetry is used for combustion reactions. I've shown you examples like you will see throughout this course and through the test and the homeworks and the laboratory material you're going to do. So from here, we end calorimetry.